All right, in this segment, we're going to consider power series and try to perform operations on power series that we would do to any other function. In particular, the operations we tend to do in calculus. So things like differentiating and integrating power series. As we're going to see, the big spoiler is we just get to do a lot of power rule differentiation and power rule anti-differentiation. So let's jump right into it. Consider this power series. Again, we're thinking of these power series as being functions of this independent variable x. And in this case, consider the power series from n equals 1 to infinity of n times x plus 2 raised to the n all over 3 to the n. So in the lingo of our previous video, we would say this power series is centered at x equals a, at x equals 2. And we would also say that all the coefficients on each successive term in our power series are given by the non-x dependent stuff here. So this would be n over 3 to the n. And the reason why I'm pointing this out here is when we think about differentiating and integrating power series, we're going to differentiate and integrate with respect to our independent variable, which is that x. So let's go ahead and just think about what it would be, what it would mean to differentiate this power series. And again, we're going to differentiate and integrate, for that matter, with respect to x. So if we want to differentiate this function or this power series, what that means is we would have this derivative operator, d dx, wanting to take a derivative of our entire power series function. Now let's take a look at this power series really fast. All of the x dependence is on that x plus 2 quantity raised to the n term. This n over 3 to the n term, there is no x dependence. So when we hit this with a derivative, the derivative is just going to bypass that n over 3 to the n, because if we're differentiating with respect to x, that n over 3 to the n just looks like a constant. And in particular, the derivative itself is a linear operator, which means if we're differentiating a sum of functions, we would differentiate each function individually and add them together. So in this case, our derivative is going to bypass the summation sign, that n over 3 to the n, and the only thing it's going to affect is that quantity x plus 2 raised to the nth power. Because again, that is where all of the x dependence is within this power series. So if we just differentiate this last term, well, this n over 3 to the n stays the same. When we differentiate the x plus 2 to the n, we would bring that n down. We would get the quantity x plus 2 now raised to the n minus first power by differentiation power rule. And we differentiate what's inside of those parentheses, the x plus 2, which when differentiated with respect to x, just gives us a 1. So when we differentiate this power series, we actually just get the following. We get an n squared coming from the original n and the n that we got from the derivative. That 3 to the n stays the same. And the only other terms there is that x plus 2 now raised to the n minus first power. So again, long story short, when we differentiate power series, we just have to differentiate the x-dependent parts. Spoiler, the same thing's going to be true for when we integrate. So let's try integrating now. And again, when we integrate power series, we're thinking about integrating them with respect to x. So let's just quickly rewrite that original power series. And we want to integrate both sides. So we want to integrate this power series. It's this infinitely long series again. And well, in a moment we're going to see we're just going to basically swap the summation sign and that integral sign. There's some very subtle reasons on why we're actually allowed to do this. This has to deal with things called uniform continuity, which you will see in real analysis. But for us in Calc B, that is way above our pay grade, so we just get to swap that integration sign and that summation. But know that there's some extra stuff going on behind the scenes. Okay. And now when we're integrating with respect to x, again, we have to investigate each of the terms in our power series. And well, the x plus 2 term, that's the only term that has any x dependence. That n over 3 to the n, that just looks like a constant for us. So our integral sign will pass that n over 3 to the n as well. And the only term it's really going to affect is that x plus 2 raised to the nth power. So again, the only thing the integral is really going to affect here is the x-dependent stuff in our power series. And we can easily anti-differentiate that using the antiderivative power rule. And we would get x plus 2. And by the antiderivative power rule, we bump up that power plus 1, divide by that power plus 1 as well. And because this is an indefinite integral, we get to tack on a plus c. So at the end of the day, when we integrated that original power series, again, what we're calling that function f of x, we just get to do an antiderivative or anti-differentiation power rule, and that gives us everything we want. So from a high 1,000-foot view, if we have a function and we have its power series representation, we can easily differentiate it and we can easily integrate it because we just get to do a bunch of power rule manipulations. Let's do another example, but this time on a very ugly, scary looking power series. And the power series we're going to consider is the following power series. This is what I'm calling script J sub 0. It is equal to the following power series from n equals 0 to infinity of minus 1 to the nth power times x to the 2n power all over a 2 to the 2n times an n factorial squared. Now, if we go through the same rigmarole we did earlier, we would notice that actually what it looks like, we are centering this power series at x equals 0. And our coefficient term now is this ugly looking negative 1 to the nth power over 2 to the 2n times an n factorial squared. And the reason why I'm writing this as j sub 0, again, my script j's might be a little goofy looking, but this is actually called a Bessel function of order 0. And there's no reason that you should know that right now. In fact, there's no reason that we should know this by name in calculus at all. But if you go on to take courses like quantum mechanics, or maybe some electromagnetic theory or partial differential equations, you might see some friends called the Bessel family of functions. This happens to be one of its family members, the Bessel function of order 0. And all we want to do is say, you know what, this looks like a scary power series. It's a power series nonetheless, so let's just go ahead and try to differentiate it. And again, we're going to differentiate it with respect to x. So let's go through the same rigmarole. When we want to differentiate this power series, we're thinking about differentiating it with respect to x. So we can bring that derivative inside of our summation. And looking ahead into this summation, the only thing it's really going to affect in this power series is that x to the 2n term. That x to the 2n term is the only term with x dependence. So it's going to bypass that negative 1 to the n. It's going to bypass that denominator that has a 2 to the 2n and an n factorial squared. And the only thing that derivative really cares about is that x to the 2n term. And look at that. It looks like we have x to some power. We just get to do a power rule differentiation. So let's go ahead and do that power rule differentiation now. So when we do that differentiation, that 2n will come down. And then we just get x to the 2n minus 1 power, since we just subtract 1 out of that power of x. And that is our derivative of the Bessel function of order 0. So again, even though this looks like a scary power series, we can differentiate it in a fairly straightforward manner. Let's go ahead and try to integrate it as well. So if we go ahead and integrate it, again, we start both sides by just writing it out. And then we can integrate both sides of our equality. So integrating the 0th order Bessel function and its power series representation. We can do the same. Again, there's that subtle issue of swapping the integral sign with the summation, but that's a little bit above our pay grade in calculus. But the Bessel function will satisfy this as well. And now we just get to look at, well, inside of this power series Bessel function representation, where is all the x dependence? And well, it hasn't changed from when we differentiated it. It's still just in that x to the 2n power. So that integral sign is going to bypass all of those scary looking terms. That negative 1 to the power of n, that 2 to the 2n, that n factorial squared. And the only thing that integral sign really cares about is that x to the 2n term. Because again, that's where all the x dependence is. So just going ahead and integrating that x to the 2n, we just get to use, yep, you've probably guessed it, the antiderivative or anti-differentiation power rule, where we bump up that power plus 1, so we get 2n plus 1, and we divide by that power plus 1 as well, divided by 2n plus 1. And again, since this is an indefinite integral, we have to tack on a plus c. So the integral of that Bessel function of order 0, again, we can just straightforwardly compute using the anti-differentiation power rule. So even if a power series looks rather scary or intimidating, we can integrate it, we can differentiate it in a very straightforward manner. So again, if we have a power series representation of a function, we can do a lot of calculus operations fairly straightforwardly, just using different power rule, whether for differentiation or for anti-differentiation. At this point, we've done some operations onto these power series, assuming that they're functions. But for functions, we want to know what x values can we actually put into the power series. Another way of saying this is, what x values give us a convergent series? And these two questions are actually one and the same. By asking ourselves what x values give us a convergent series, what that's saying is, hey, give your function or your power series an input x. If that power series converges with x, it's going to pass back one specific output. So by doing these types of questions, we actually figure out what is the domain of that power series. So check out the next video.